Hello students, this is my 7th lecture of Control System 2 followed by the code EE603. I am Priyanjali Mukherjee, Assistant Professor Electrical Engineering Department of Narula Institute of Technology. In this class, we will discuss on the system realization, that is the canonical forms of the state variable equations. So the contents are the system realization, the canonical form or the controllable canonical form, example of controllable canonical form, observation from the controllable canonical form, the observable canonical form, its example, the relationship between observable and controllable canonical realization, diagonal canonical form, example of the diagonal canonical form, the references and MCQ question. First is system realizations. So we shall determine the state variable model when the transfer function is given. Now the state variable representation is not unique. There are an infinite number of ways to writing the state equation. So we can consider some methods for deriving a set of state variable representations from the transfer function. So the transfer function is related to the matrices in the state space. Using the formula, the transfer function is equal to C into Si minus A inverse into B. So we will write that how many choices of this A, B and C can be produced the same transfer function, or we will see that there are multiple models or the realization that correspond to the same transfer function. That is known as the system realization. Among these three, the controllable canonical form is used in the most of the cases. So when we are going to derive the state model from the different representations of the system, it can be represented in mainly three forms. One is in the physical variable form, second one is the phase variable form, and third one is the canonical variable form. So we have already discussed the physical variable form and the phase variable form in the previous videos. Now the canonical variable form can be classified as the controllable canonical form, observable canonical form, diagonal canonical form. There is one more form is also there, that is the Jordan canonical form, but here we will discuss only the controllable, observable and the diagonal canonical form. So first one is the controllable canonical form. So this form is generally useful for the controller designing using the pole placement technique. The transformation of this system to companion form is based on the controllability matrix, which is generally numerically singular, and we will avoid using this controllable form for the computation if possible. Now for this one is the transfer function general form, which is defined as the Qs by Pus, where Qs is the output of the system and it is the Laplace transform of the output, and that is equal to B0 s to the power n plus B1 s to the power n minus 1 plus n minus 1 into s plus Bn divided by s to the power n plus A1 s to the power n minus 1 up to an minus 1 into s plus A0. So in controllable canonical form, this transfer function can be written by the multiplication of two terms. So this Qs by Ps can be written as Qs by Rs into Rs by Ps. In this form, we can write the same transfer function. So next, we will consider the transfer function, and then we will use the cross multiplication method, and we will write the differential equation corresponding to that equation. Then we will assign the state variables and we will get the result matrix A is equal to 0 1 0 up to n, then 0 0 1 up to n, that will be 0. In this way, at the last row we are getting the coefficient of the denominators, that is minus of an, then minus of an minus 1, then minus of an minus 2, and the final one is the minus a1. So this form is known as the controllable canonical form. Whereas from the output equation we can find out from in standard vector matrix form that B equal to 0 0 up to 1, and the C becomes this Bn minus An B0, Bn minus 1 minus An minus 1 into B0, and so on. So from this controllable canonical form we can easily find out what are the actual coefficients of the denominator, and then if we look this, then we can write what will be the matrix A, B and C. So let us take one example. So here one state space representation we need to find out in the controllable canonical form. The transfer function is given as s plus 3 divided by s square plus 3s plus 2. So if we compare this by inspection method with the general form of this transfer function, then we can say that the a1 it becomes 1, then a2 is equal to 2, and b0 becomes 0, b1 is equal to 1 and b2 is equal to 3. So we can write the state space equation in this form, that 0 1, and the next row we will write the coefficients of a1 and a2 in the negative form. So the coefficient of a2 is equal to minus 2 and coefficient of a1 is equal to minus 3. So we have got the matrix A equal to 0 1 minus 2 and minus 3. Similarly, for the B matrix it will be 0 and 1 as it is a 2 by 2 matrix. So and next, for if we consider the output equation, and then we can find out y is equal to bn minus b0 into an. That will be the first term. So bn, here n is equal to 2, so b2 is equal to 3, and then the next term, that is bn minus 1, here n is equal to 2, so n minus 1 is equal to 1, so b1 becomes 1. So the C matrix becomes 3 and 1. So by the inspection we can easily find out the controllable canonical form from the given transfer function. Next is what are the observations from the controllable canonical form. So here we can see that each of the denominator coefficient which shows the negative and it reverse order in the bottom row of the A matrix or the system matrix, and the B matrix consists all the zeros and the last entry is 1, and the C matrix has the numerator coefficients in the reverse order. And among these observation, the most important one is that the coefficient of denominator polynomial are readily available in this form. That means if we can remember the general form of the transfer function, then by inspection we can easily write down the controllable canonical form from the given system. Next is the observable canonical form. Now the observable canonical form, which can also be used in the analyzing and designing of the control system. And if a system is observable, then its all states can be determined from the output. So now what is the observable form? So look at here, if we consider the x dot equal to ax plus bu, then the last row has been shifted to the last column. That means the matrix has been transposed. And similarly, the B matrix has been observed as Bn minus An B0, Bn minus 1 up to An minus 1 B0, and finally B1 minus A1 B0. And Y is 0 0 up to 0 1. It will be dependent upon the order of the system, and D is equal to B0. So this form is known as the observable canonical form. So here also we can check the equation of the general form of the transfer function, and then we will compare the coefficients of the numerator and denominator. Then we will just put in this form, then we will find out the observable canonical form. So this is an example of observable canonical form. Here also the highest power of the S becomes 2. So the order of the system is equal to 2, or n is equal to 2. So if the n is equal to 2, then we will find out A1 is equal to 3 and B1 is equal to 1. A2 is equal to 2 and B2 is equal to 3 and B0 is equal to 0. So now we will write the observable canonical form. Now n becomes 2, that's why there are two state variables, and these are the first derivative of state variables x1 dot and x2 dot, and that is equal to 0 1. Then in the observable canonical form it will be minus of an. So here n equal to 2. So we will write here minus of A2. So A2 is 2. So minus of A2 represents minus 2. And the next one will be minus of An minus 1. So n is equal to 2 and n minus 1 means 1. So minus of A1 will be here. Now A1 has been, we have find out 3. So minus of A1 becomes minus 3. So in the same way, we can find out that B matrix, it will be the Bn, that is B of 2, and this is B1, that is 3 and 1. And similarly, Y is equal to 0 and 1, as we can get inspection from the previous cases. So this one is the observable canonical form, where we are getting that all the coefficients of the denominator has been written in the last column of the given system. So this is the relationship between the observable and controllable canonical form realization. So first one is the CCF. Now to draw this CCF diagram, we have to remember that for the controllable canonical form, the variables has been rearranged in the increasing order. That is this one is the x1, so x2 will be here. So sorry, it is decreasing order, that is xn, then xn dot, then after integration it will have xn, then xn minus 1 up to x2, and then x1, and x1 is equal to b0 into y. So in the controllable canonical form, the state variables has been assigned in the decreasing order. Whereas if we consider the observable canonical form, then we can see that the state variables which we have assigned, those has been written in the increasing order. So the first one is x1 dot, then after the integration we were getting x1, then the state variable is x2 dot. After that integration it becomes x2 like this, and the final one is xn dot. So that means this controllable canonical form is just the mirror image of the observable canonical form. So whatever the matrix, system matrix we are getting at the controllable canonical form and the observable canonical form, those are the transpose of each other. That means this system matrix is AC, which is obtained from the controllable canonical form, and that is equal to A0 transpose. This A0 is the system matrix which has been obtained from the observable canonical form. Next is the B matrix. Similarly, from the controllable canonical form, the B matrix is written as BC, and here we are getting the C matrix, and B matrix is the transpose of the C observable form. Similarly, C of controllable form is equal to B matrix of observable form and its transpose. And finally, the D in case of CCF is equal to D of the OCF. So we can say that the CCF and OCF are just the mirror image. Next is the diagonal canonical form. So here the diagonal canonical form in a state space model where the poles of the transfer function has been arranged diagonally in the system matrix. Now the system transfer function have a denominator polynomial which can be factored into distinct roots. So if the system has distinct roots, then we can use the diagonal canonical form. So we can write the form in this way, and if the transfer function can be written here in this way, so we can use the partial fraction expansion method, and then we can write the transfer function is equal to b0 plus c1 by s plus p1, c2 divided by s plus p2 plus cn divided by s plus pn. So in this way, if we model the system, or we can draw the system diagram from the given transfer function, and we will rewrite the system equations, then we can see in the diagonal canonical form all the poles, locations or the roots are written here in the diagonal elements. As in diagonal elements, we are getting these poles which are actually distinct. That means the P1 should not be is equal to P2, should not be is equal to up to Pn. So each roots will be distinct. Then we can find out the diagonal canonical form state model. And the C matrix becomes C1, C2 up to Cn. So next, take an example of diagonal canonical form. Here we can write this equation s plus 3 divided by s square plus 3s plus 2. In this way, s plus 3 divided by s plus 1 and s plus 2. Now we will use the partial fraction expansion method, and then we can write down this s plus 3 by s plus 1 into s plus 2 is equal to 2 divided by s plus 1 plus 1 divided by s plus 2. So C1 becomes 2 and C2 becomes 1. So the diagonal form will be, the pole locations here will be there in the main diagonal, that is minus of 1 and minus of 2. And B matrix will be 1, 1, and C matrix will be the value of C1 and C2. So C1 is equal to 2 and C2 is equal to 1. So this is the diagonal canonical form. So for the same transfer function, we can use the different methods. One is the controllable canonical form, another is the observable canonical form. or the final one is the diagonal canonical form. That means all of these representations gives us the same transfer function, or we can say that these three are different ways of writing the state equation which actually represents the same transfer function. So these are my references. So I hope after this video lecture you have a clear idea about today's topic. Now we will go through some question answer session in context of this video lecture, and you are requested to go through it gradually and solve the MCQs by your own. Also the answers are attached at the end of each question.